And again, I'd like to welcome all of you here. This is a joint event with our Southern Vermont Natural History Museum and the Hogback Mountain Conservation Association. And you know, when you plan these, I apologize, we don't have enough chairs. You never know how many people are going to come. And I should have expected it because, after all, we do have a rock star who's going to be leading the discussion today. But welcome, everyone. I suspect that, like many of you, is here because Hogback really is a special place. Or maybe you saw this at the Mount Snow facility and got sent down today. But Hogback, think about you know, what a special place it may be for you, and for me, you might think about skiing. Well, the ski slopes were actually on Mount Olga, and Olga was Olga Haslund, who was my uncle's godmother. My roots go back quite a bit. Both my parents were born here in Wilmington, and I really remember and have great fondness and love for the place. And actually, my mother worked at the museum with the not the museum, at the restaurant. She was would bring people in, and so this was really a special place for us. And as I said, we do have a rock star today. Roger Haydock is our speaker, and Roger is a really enthusiastic and very knowledgeable guy. He's self-taught in geology, and if you want to know some of the finer aspects of Roger's history, I encourage you to look online for the Brattleboro TV. They did an interview of him that lasted about a half hour, and he has a very, very unusual background, mostly in film, but the story begins in high school, and I think what you're going to see with geology is a continuation of that. He's a self-taught individual. He's worked, as I said, in films. He's been involved for many years with PBS and all the other networks, Frontline, and then in recent years he's been retired and still going around developing trails. Who better than a geologist to figure out, you know, where to make your trails here in Vermont? But I think you're going to be pleased to hear what Roger has to say in a very creative and interesting way. So Roger, we're delighted to have you, and thank you for coming.
Well, thank you. I'm an amateur geologist, and the word amateur comes from Latin, a word that means somebody who loves their subject, and that's me. So today we're going to look back at least 500 million years, look with some enthusiasm, we hope, at the history of the geology of southern Vermont. And if we go far enough back, we're going to start with first principles, though. Okay, so the Earth is spherical in shape, yes? And the Earth, as you might imagine, is made out of the various elements, the physical elements. There are lighter weight elements like nitrogen, oxygen, carbon. Then there are the heavier elements, iron and nickel. Gravity holds all these elements together on the Earth, and gravity tugs the heavier elements towards the center of the Earth, meaning that the lighter elements float along the surface. The very lightest elements would be oxygen, nitrogen, that form our atmosphere, yes, and they ring the planet. And then another lightweight element or set of elements that rings the planet is our water, right? The oceans. 70% of the Earth's surface is ocean, and water is lighter than rock, so yes, it forms the surface. And then we have the continents. The continents are made of rock, and we humans think of rock as being heavy, right? About 3 times as heavy as water. And so we don't think of continents as being light, but continents are made out of rock that's lighter than what the continents are floating upon. And so the continents actually are floating on the surface of the Earth as rafts of rock that float. And the rock that most of the continents are made out of, if you dig far enough down, you always get to granite, okay? So the granite is beneath us. It's not usually at the surface. It sometimes is, but right here there's no granite right at the surface. But if we drill down far enough, yes, we'd hit granite. And granite comes in different flavors that have different actual geological names, but they're all in the granite family, kind of like the different brands of granola cereal are all somewhat different in their ingredients, but they're all granolas. It's the same with the granites. So we're on these rafts of granite that are floating on the surface, and they're floating on something that's denser, heavier than they are. Beginning roughly 460 million years ago, up to about 250 million years ago, our continent was moving relatively eastward and was crunching into various things. There was a series of landmass collisions that created the Appalachian Mountains that are kind of like pressure ridges, crunch, crunch, crunch. For the last 200 million years, our continent has, generally speaking, been moving westward, and so the crunching has been happening all along the western boundary of North America and South America as well. Here you can see, it really just looks like somebody shoved all this stuff up against North America, and guess what? Somebody did, right? Only it wasn't a buddy, it was just land masses. So if we go back 460 million years ago, which is only about 11% of the history of the Earth is 4.6 billion years old. I guess that's 10% of the history of the Earth. If we go back 10% of the history of the Earth, North America was not north of the equator then. North America was down where South America is today, and southern Vermont was where Rio de Janeiro is today. And if we'd been in Manchester or Bennington back then, it would have looked, well, something like this. Well, there were no swimming pools, no tourists, no condos, no palm trees, no beach umbrellas. What part of this picture was what western Vermont looked like 460 million years ago? This upper right corner. Western Vermont at that time was shallow water, tropical, marine environment where you could have gone snorkeling. Yes, you might not have seen the kind of swimming creatures we have today, but that's what western Vermont was. It had various animals that left fossils. These are brachiopods. Brachiopods were once very common, now they're very rare. There were trilobites. Trilobites today don't exist anywhere. They've gone completely. And what happened in that shoreline out there, which was to the west of us, in the shallow water areas, is year after year after year, deposits would occur of a rock called calcium carbonate, which dissolves naturally out of seawater or out of warm water when it's shallow. And so that year by year by year, storm by storm by storm, would form layers out there. And then came the first of our land mass collisions. Okay, this requires a bit of imagination. Here is the basement rock of North America, the really old rock that's under everything, the granite, okay? Here's the shallow water tropical marine environment where you could go snorkeling. Out to the east was deeper water. This is the continental shelf, this was underwater. And out to the east were deep ocean muds. And there was also a little bit of volcanic deposit. And along came an offshore volcanic island chain and pushed some of these rocks westward. These ones, the rocks that originated in deep ocean mud, made it all the way out to Bennington, all the way out to Manchester, sitting on top of the calcium carbonate rocks that have turned into marble since they got metamorphosed today. But so you have shallow water rock upon which deep water rock landed. It was shoved. And that created the Tectonic Mountains. Some of those tectonic rocks were trying to get all the way to Manchester to do some shopping with their friends, but they didn't make it, got stuck here about halfway across the state, turned into Hogback Mountain, turned into Mount Snow, turned into Haystack Mountain. Okay, so that was 460 million years ago, and here you can see this is the shoving of those rocks on that cross section. And so here you can see this is amphibolite. This is the rock that's right here where we're going to go walking today, though we won't see much because it's not really exposed where we're going to walk. But this was a volcanic rock, and you can see they started out parallel horizontal, but in the folding and shoving they got pushed, levered upwards a little bit and folded. These rocks were laid down originally horizontal. They got shoved up to where they're on an angle. And this is Equinox Mountain in Manchester, seen from the east on Route 30. The village of Manchester's down here. Here's the high mountain. You're all used to the idea that above a certain elevation you get spruces and firs on our high mountains, and below that you have deciduous trees. That's not unusual, but what is unusual here is that this line where the conifer trees, the spruces and firs, begin and the deciduous trees are separated from them is also the bedrock line between the rich bedrock that today is marble, where sugar maples are abounding, and then above that is the more acidic rock, which is a slate or a phyllite, and it has the spruces and firs. And so here the bedrock difference is completely controlling the plant communities. So when you take calcium carbonate and cook it and just make a rock out of it, you get limestone. But if you cook limestone, you get a rock called marble. Yes, and marble is crystallized limestone. Chemically, they're just the same. And the marble that is at the base of Mount Equinox is also found at the base of another tectonic mountain in Massachusetts called Mount Greylock. And guess what gets mined at the base of Mount Greylock? Tums. Tums is mined rock from 460 million year old sea bottom, shallow water sea bottom, and there's a mine there where they're mining it out. And think of it, in our high-tech society, as everybody's getting stuck in traffic, and God, I'm late, oh damn it, popping Tums, you know, to get their stomach down. On their behalf, at the same time, they're not thinking about it, but slowly the base of Mount Greylock is being eroded by their stomach acid, indirectly. And now in geology, there are many causes of erosion. Usually it's rain and water. Ice can do it. There's wind erosion. I have yet to read a geology book that mentions that stomach acid, sometimes human stomach acid, can sometimes be eating away at our mountains. But Tums, when you eat it, you're eating a little bit of the base of a tectonic mountain. Okay, now, although our geology these days is not so exciting, if we go back any length of time, things were more exciting. So we're going back now. So we were 460 million years ago. So now we're going to go back about very roughly 400 million years ago. And what was happening? Well, this area of North America was eroding out into the ocean. Down would come a layer of sand. How about some volcanic eruption? There was a little bit of that. Then we've got some limey mud, layer upon layer in the deep ocean, okay, kind of like the pages of a book, and then just straight old mud, okay, so that's what you would find offshore. This is roughly 400 million years ago, so now I need a volunteer who's going to impersonate a microcontinent. Now, it's called Avalonia. And we've a little oversimplified it here, as you might be able to tell. But I need somebody who wants to be Avalonia. It's only going to last 400 million years. Come on. Just one person. Yes, up you go. All you have to do is go to that end of the table. Okay, start, just push. Push the rocks. Push them. Just keep coming. Keep coming. Okay, keep coming, keep coming, keep coming. All right, and you keep coming a little bit. Okay, very good. That's excellent. You don't have to do anything for the next 400 million years. You're going to just be quiet, you know, don't make a mess. You are now eastern Massachusetts, Rhode Island, down East Maine, part of the Maritimes, even part of Great Britain and Ireland. These are the rocks of eastern Windham County. They are folded over like this, okay? Okay, so now we have southern Vermont, all here. We could go driving. let's start at Bennington or Manchester. Here's the valley of Vermont. The marble has eroded out that valley because it's softer in the chemical erosion that happens with rainwater. It dissolves out the Tums Rock, so there's a valley there. Then you have the basement rock of the Southern Green Mountains, the really old rock. It's over 1 billion years old. When you drive west from Wilmington and you go up that big high hill, once you get past the road to Somerset Reservoir, those rocks are over 1 billion years old, so you're hitting those ones. Then to the east of that, you get Mount Snow and Haystack and Hogback. And then the east of that, you get the youngest rock in our collection, which goes all the way down to Brattleboro. And these rocks are folded quite heavily. Some of them are flopped over. And here, you can see a more professional representation of the same thing. This is eastern Vermont, you know, the eastern county, all folded. Then you get the basement rock, the highest Green Mountains, and then out to Bennington, out to Manchester there. So that happened around 400 million years ago. And that basically was the last time things got really exciting from a collision standpoint around here. But it was a pretty big deal. This is a cross-section maybe 25 miles north of us. Look at these rocks. They came over like a breaking wave. The geology writer John McPhee has described a mountain ranges as being a wave of rock that takes 10 million years to break. And this is in Chester. So these rocks came in like this, then they come in, whoa, like whomp. Just like you're going surfing in Hawaii, only it's with rock. These two rocks are two different formations, okay? The greenish-gray one and the black one, they were laid down originally horizontal. They're now perfectly vertical. This is up near Springfield, Vermont. Here, all up and down Interstate 91, you see this lustrous rock, this phyllite or schist that kind of looks like the dull side of Reynolds wrap, aluminum foil. Well, guess what? It's got a lot of aluminum. That's mica, okay? That's making it shine like that. And it originated as deep ocean clay that was cooked and compressed to mica. So if you take clay and compress it a little bit and cook it a little bit, you get mica. But if you cook it a little bit further, you get these bumpy things that kind of look like the rock has some acne. The rock does not have acne. Those are garnets. These are cranberry colored. It's a little hard to see in this light, but those minerals will form if the rock gets cooked a little further than it needed to get cooked to create mica. This is similar to what would happen if you took a piece of white bread, Wonder Bread, and didn't put it into the toaster at all, it's white. Put it into the toaster for a little bit, it's golden brown. A little longer, it's really dark brown. Put it way in for too long, it's charcoal. When you take these 4 pieces of bread out, you can tell just by looking at them how long they were cooked. Geologists can do just the same thing with these minerals that tell them how much the rock was cooked. So garnets mean they were cooked more. And if we go on the walk today and the snow hasn't covered the rocks, we'll see some examples of rock that has garnet that was cooked. And then there are other rocks that don't have garnet, that weren't cooked enough. It may all be covered with snow, so we might not see that, but it's there to be seen, at least when the snow's not on the ground. So this is a bedrock map of southeastern Vermont. It's just east of where we are. And here's the Connecticut River going up. Here's Brattleboro's down here. Black Mountain in Dummerston is here. Bellows Falls is here. That's Mount Ascutney way up there. And I think you can, if you just use your intuition, you can sort of see that, boy, doesn't it look like these rocks kind of folded and did something like that, right? These are all hard rocks, but their shape certainly suggests they were folding and doing funny things in the past. And that's because when these rocks were folded like this, they were deep underground where they warmed up and they got softer, and so they could fold in a way that today they wouldn't because they're so brittle when they're at the surface.
Is there a reason why the New Hampshire side is just...
Oh, absolutely.
Yeah.
Politicians get elected in New Hampshire. No, I'm being a little facetious, saying they're going to keep the taxes down, right? So if you're going to get the taxes down, you don't get all the surface. I'm being a little facetious. You don't get all the surfaces. So over here in the New Hampshire side, they didn't get any coverage. But here on the Vermont side, we do. So it's white. It's white only because it's looking at Vermont.
Oh, the reason I'm asking is like if you go up Putney Mountain, there's such an obvious geographical difference from the west side where the Green Mountains are and the east side where New Hampshire's, it's much flatter. And there's always this, you know, I'm not being a geologist, there's often this, you hear this story about New Hampshire and certain parts of Rhode Island and Connecticut actually being once part of the continental drift. And
That's right.
Supposedly along the Connecticut River, there's even mineral deposits that are exclusive from a very specific area of the African coast.
Well, let me just continue because your question is exactly right. So I'll just be answering that. Basically, these different colors, let me back up a little bit. The different colored rocks here, the different colors represent different kinds of rock. And as you can see, they're all going north-south because we were run into from the east by Avalonia. And so the rocks that are on the New Hampshire side are different, and we'll be getting to that in just a second. This is Putney and Westminster here. You have the different colored rocks on this geological map. The top of Putney Mountain is right along there. Connecticut River is right here. Here you have rock that, although it's technically in the state of Vermont, is really New Hampshire affinity bedrock, okay? Just like think Interstate 91 approximates the boundary between the two states, but it's not exact. So also the geology of difference approximates the exact border, but it's not precise. So this is the eastern part of Putney, eastern part of Westminster. And if we look here at this false color photo that shows the different vegetation types in different colors, with dark red being the conifer trees like hemlocks and white pines, this gray-green being the deciduous trees, and then this whitish things are the fields. You can see here, this has a very different vegetation pattern than this area. This area is loaded with fields. This area is loaded with hemlocks and oaks. So if we go back, you can see that the bedrock is completely different. This has tums in it, basically, calcium carbonate, that came as underwater landslides off the shallow water of the shore of North America. And so it makes a rich soil. Over here, you have an acid bedrock. This was deeper out into the ocean where the underwater landslides bringing the tums material never reached. And so it was a mud originally, a very acidic bedrock, meaning an acidic soil, meaning hemlocks love it, farmers don't, and farmers love this material, okay? And then here you can see in the Connecticut Valley itself, the rich soils in the river bottoms are pretty independent of the bedrock, right? There's just so much of it. So in the acid areas, you find some bedrock that'll look like that. You'll find lots of hemlocks. I mean, hemlocks will grow in many places, but they will compete most effectively where it's already acid, and they make the soil even more acid with their needles. And then we come over here to this rich zone, which is the western part of Putney, Westminster West, where you have lots of fields. And one of the rocks that characterizes that area is an impure marble. It doesn't look like marble at all, but it crumbles in your fingers, okay? You can crumble that stuff. And that's because the calcium carbonate is dissolving away, that's holding the grains of sand together that are in the rock. The calcium carbonate dissolves away in the natural acidity of rainwater. Rainwater was acid even before we humans made it more acid. And so in a humid climate like we have, marble dissolves away in the rainwater. If you go out west where it doesn't rain much, marble or limestone, they don't get rained on, they're a hard rock. Around here, they're a soft rock, so that depends on the rainfall. And so where you find this rock, moss will be growing like on a stone wall that has some of this stuff. Plants love it, you know. And one of the plants that really indicates you have rich soil is the maidenhair fern. So that means you've got super rich soil. If you find that growing, and it has black stems, which this picture doesn't show, but of the ferns that you find, they're the ones with black stems. You've hit the jackpot, if you're a plant. So this is the farming that's more common where you have that rock. It's called the Waits River Formation, by the way. It runs all up and down the state. It's even more widespread further north in the eastern part of the state. And then here on, this is again Putney Mountain, Windmill Hill here, West River down here, Connecticut's over here. Right along the spine, you can see there aren't any fields up there. It's yet a different bedrock that doesn't have the impure marbles in it, and it has relatively more quartz, right, which breaks down only with difficulty into soil, and it breaks down into sand. So it's not great for plants, and you can see just scrawny plants are growing there. And then a fourth rock that you can find along that ridge is a black rock called amphibolite, which is the same rock we have over here, but a different formation of it. And its origin is volcanic, okay? And because it's such a distinctive black rock, it really stands out. Where it's exposed, it makes it very easy for geologists to see the underlying folds and everything. It's like striped toothpaste, you know, you can tell the shape by the stripe. And so this is amphibolite. So that's on top of Putney Mountain, right next to some quartzite. And then one other thing that happened as a part of this Avalonian collision that folded these rocks here is some of the rock got dragged way down, called subducted, 50 miles underground, to where it got so hot, it formed these hot globules of hot molten magma that then rose up, because they're hot, heat rises, right, trying to get to the surface. If they get to the surface, you have an explosive volcano. But if they don't get to the surface and just get stuck, they can cool and congeal into the rock we call granite. And that's Black Mountain in Dummerston. So it originally formed more than 4 miles underground. Granite always forms more than 4 miles underground. I think this one they're thinking like 11 miles down or something. But today it's at the surface, so that's in 380 million years. There's been enough erosion to erode away, 12 miles or so of overlying rock. Now, if you do the arithmetic, you think 12 miles times 5,000 feet, that implies that mountains were 60,000 feet high. Well, no mountains today are 60,000 feet high, and we don't think they were 60,000 feet high back then. What happens? Well, think back to the fact that the continents are floating on the surface like ice flows, okay? They're like a floating raft on a swimming pool in the summertime, okay? And where the continents, where land masses run into each other, there's some up movement here, but most of what crunches when land masses run into each other builds up down below, because kind of like ice flows that are 90% below the water surface and 10% above. So you get a big thickness of continental crust where the mountains are happening. And so then what happens is, think of an inflatable raft in the summertime, and the mountain ranges here are 2 six-packs of Coca-Cola. As you erode away one of the 6-packs, so the mountains are getting a little lower, the rest of the raft rises up, floats up. Pull the other one away, it rises up yet again. So what can happen is you could have a mountain range that might only be 20,000, 15,000 feet high or something, keep eroding away a lot of rock, erode away 5 feet, but you get a 4 feet of rebound, 5 feet, pull away, 4 feet of rebound. So it just keeps rebounding, rebounding, rebounding. So eventually, rock that started out very deep underground can emerge at the surface. And so you can erode away 60,000 feet of mountain, but without the mountains ever having been that high. So this is near that Black Mountain. This is a bit of the hot molten lava that came up through cracks as superheated steam rock coming in through the surrounding country rock. Here you can see the size of the grain. The crystals are very small. That tells you it cooled really fast. Okay, if the crystals get really big, it's because they had a long time to form. These cooled really fast. And here, this is an abandoned granite quarry on Black Mountain. And here's the mountain itself. It's steep. And you can see these parallel lines. And it's easy to imagine, oh, the quarrymen must have made these. It looks so organized. But no, this is a natural phenomenon. It's called decompression fracturing, and the reason it's happening is that when this rock originally formed miles underground, it was under thousands of atmospheres of pressure. Huge. Think of all the weight. But as the overlying rock has eroded away over the years, finally that pressure is getting released, and it gets released parallel to the surface of the Earth. Since here the surface of the Earth is sloping, so are the decompression fractures sloping. If you go up to the big granite quarry in Barry, where the landscape is flat, the quarry goes down into the earth, you'll see those decompression fractures, but they're all horizontal because that's the surface that they're rebounding up to, where the pressure is released. So on a hilly place, you get the lines like this, but on a flat place, those decompression fractures would be flat too. So that's in Black Mountain in Granite, in Dummerston. So, the first plants may have been growing here, but we don't have a record of it because the rocks that we have here don't contain fossils, okay? But as the mountains were eroding from here out in upstate New York, where was our erosion going? It was going right out there, and upstate New York abounds in fossils that were created at the same time that our mountains were eroding. So for like 375 million years ago, the indirect ancestors of this tiny plant called a lycopodium grew up in New York State to 100 feet high. And there are fossils of it. You can find fossil tree trunks out, where they've found them there. We probably had them here too, but everything's eroded away. We don't have the rocks that record that. Upstate New York is like a photo album of what the environments were at that time, but we don't have it. So this is a lycopodium. It's colloquially called a ground pine, but it's not related to pines. It is an evergreen, but not a pine. Ferns came in, right? There were plants known as tree ferns, and they still exist in some places. This is on the island of Fiji, and they were very common 375 million years ago. There's a geologist from 375 million years ago. Okay, so this is a combination of bedrock map of Vermont over here, New Hampshire over here, and as we drive east on Route 9 from Vermont, starting in Bennington and all the way into New Hampshire, continuing across, we basically are shifting from rocks that are not terribly acid towards rocks that progressively, though unevenly, get more and more acid, reflecting the fact that originally we were close to the old shoreline of North America. We got the benefit of the underwater landslides of the calcium carbonate rich rock, the Tums, but further out to sea in New Hampshire, the rocks were more acid. They didn't have that. And so you have different bedrocks, different acidity, different plants. So in the New Hampshire area, you have tons of oaks. Oaks do well in acid conditions, no problem, they thrive. You have mountain laurels. Now, if you look in Windham County, there's some mountain laurels on Black Mountain. There's mountain laurels in Vernon. Why are they in Vernon, but they're not in Guilford? It's because the bedrock line between the acid rocks of New Hampshire affinity and the less acid rocks of Vermont runs right about down to Interstate 91. So east of that, you get New Hampshire affinity bedrock. You also might notice you have sometimes New Hampshire affinity politics too. Okay, so where you have the sandier soils on the east side of the Connecticut River, you get white pine. And then on the Vermont side, we generally speaking have richer soils, and a tree species that just flourishes in rich soil is our sugar maple, right? So the most common maple in Vermont with its better soils is the sugar maple. The most common maple in New Hampshire is the red maple, which isn't so finicky. We get white ash, and then, let's see, the last collision that happened to North America coming from the east didn't really affect New England as much as the earlier ones had. The effect was bigger to the south, the southern Appalachians, Pennsylvania, and southwards down there. But what happened is that Morocco, the shoulder of Morocco, rammed into New England. Okay? So here would have been Morocco. I think Marrakech would be about here. Okay, so 200 million years ago or so, if you had a car, you could have driven to Marrakech, right? Easily. So, and at that point, then there was no more ocean between us and the eastern continents, and in fact, the whole world had coalesced into a single supercontinent known as Pangaea, okay, and that was around 200 million years ago. And you can find excellent evidence for that down in Massachusetts, just south of the Mass border. The lower Connecticut River Valley abounds in sedimentary rock that comes from that era of 200 million years ago, and we have down there some of the best collection of dinosaur footprints anywhere. And they're so abundant that scientists are able to do statistical analysis of it, and that's meaningful. And so they've been able to do a lot of richer deducing because they have just so much evidence to work with. So this is just south of us down in Gill, Massachusetts. Here you can see this is rock that originated as mud. Here, this is a road cut that maybe isn't too clear, but this was a flash flood at a time when the climate around here was semi-arid. We were just a little bit north of the equator at that point, so our continent had been drifting northwards. And it was not unlike, say, Nevada or something like that, where it's mostly very dry, but occasionally you will get a big flash flood, bringing just huge amounts of erosion coming down. Here you can see dinosaur footprints. This is right on Route 2 in Massachusetts at a road cut. You or a 6-year-old could put their finger in a footprint that was left by a small dinosaur about 200 million years ago on a very specific day, on a very specific purpose, whatever the dinosaur was trying to do.
What town is it?
Gill. It's
On Route 2?
yeah,
Oh.
yeah. You just have to go look for it. And here's another one, right? So yeah, and if you go scouting around that area, and I didn't bring pictures of it, you can find some places where there's little raindrop craters from it falling on sand, you know, like it would make, right? Tiny raindrop crater from 200 million years ago, absolutely perfectly preserved. So much of the history is missing, and then you have this super detailed picture of the landscape from 200 or so million years ago. Here you can see some ripples, right? It was underwater. So then, around 200 million years ago, the continents began to split apart again, okay? And all up and down the east coast of North America, rift valleys would start to happen. Kind of like what you find in East Africa today, they have a rift valley. The Red Sea is a rift valley. The Dead Sea east of Israel is a rift valley where things are splitting apart. The lower Connecticut River Valley is a rift valley that started to open and then stopped, okay? And so the rocks that had started out horizontal, as things got stretched, they got tilted a little bit. And all up and down the east coast, you have rift valleys. There's one in Gettysburg. The South may have lost the Civil War because of Little Round Top, I think it was called, that was a mountain created by the rift valleys. Most of those rift valleys stopped opening, but one rift valley has never stopped opening in 200 million years. We don't call it a rift valley anymore. We call it the Atlantic Ocean. It's still opening at about an inch a year. So in my 69 years on this planet, I'm now 69 inches further away from Europe than when I started. I expect the airfares will go up. Okay, as our continent started moving westward, we may have gone over hot spots, okay, like Hawaii today is hot spots. And so there's quite a bit of volcanic activity that occurred in the White Mountains, in New Hampshire, say 125, 150 million years ago, as we were moving westward. And here in Vermont, eastern Vermont, we have a mountain, Mount Ascutney, with 3,000 feet high today. 125 million years ago, it was maybe 15 or 20,000 feet high, okay? And it was an explosive volcano that erupted at least twice And so if we'd been here 125 million years ago or so, we would have seen the dinosaurs running away towards us on the interstate here. So go back more than 125 million years ago, and the kinds of plants that were common were not exactly the same as our plants today, but they were like conifers, okay? What we didn't have were the flowering plants. They came in more recently, okay? So they're a more recent addition as, right, that's as far as we got on that one. Okay, now we're going to go to maybe 70 million years ago, and this is only a guess. Well, I guess it doesn't work on this one. You can't see a thing because this is too dark. But anyway, our landscape around here looked maybe something like that. It was a low-lying flat landscape, and then sometime within the last 70 million years, and the dates are very vague on it, the landscape was uplifted, and you can't really see it because it's so bright in here, but this is a river valley down here, and so the summits are still showing that old relatively flat land surface from when we were close to sea level, maybe 70 million years ago, question mark on the date. But then the land was uplifted. The rivers have had enough time to erode out 1,000-foot deep valleys, but the summits still maintain that old peneplain structure. It's called almost plain structure, peneplain. Here's a view right from Hogback, and you can see that the summits, if you just mentally connected them and filled in the valleys, it would be a pretty flat landscape. So we're an uplifted plateau that's then been eroded. So that's the interior part of New England. If you go to the coastline in New England, what's happened is that at the same time that the interior was uplifting, the coasts got depressed. So we have a flooded coastline. Narragansett Bay in Rhode Island is a flooded river valley, right? The coast of down east Maine is all flooded river valleys. New York City, the Hudson is a flooded river valley. So the interior sections got bowed upwards. The shoreline sections have been bowed downwards. If we go back to about 5 million years ago, our climate was warmer than it is right now, okay? And we had a climate not unlike Virginia or North Carolina today. And although the glacier since then has stolen most of our topsoil, there are places where you can still find some of that pre-glacial soil. And this is over in Harrisville, New Hampshire. It's sort of reddish gray. It's called saprolite. It has no little pebbles in it, no little cobbles. Like most of our soil is all you're just finding rocks, rocks, rocks. Not this ancient soil, which was from a southerly type climate, and it's a southerly type of soil. Usually that's hard to find at the surface, but occasionally you find an outcrop of it. So, beginning around 2.5 million years ago, the climate began to get a little chillier, okay? And up in north of Quebec City, there's some mountains up there, and they get a lot of snow even now, because when I was up there like 6 years ago, we didn't get quite all the way that far north, but the people told us the snow was standing 13 feet deep on the ground. So it really snows up there. And so 2.5 million years ago, it was snowing up there too. And it would snow so much that even in the summertime, it wouldn't melt. And when that happens and it starts building up, once it turns to ice, and then once ice gets more than 50 or 100 feet thick, ice that's brittle at less elevation, when it gets thicker than 50 or 100 feet, it becomes plastic and starts to flow. And ice began to come down from Quebec to New England, reaching ultimately Long Island, Martha's Vineyard, Nantucket. And there have been at least 16 separate ice advances and retreats in the last 2.5 million years, 4 of which reached all the way down to here. The most recent one was only 18,000 years ago at the peak, and it didn't go quite as far as the one from 120,000 years ago had gone, but almost exactly the same. As the ice would flow southward, it would sort of smooth out the north side of a hill and then pluck rocks from the south side of hills. So north side would be more gradual, south side commonly having cliffs. as the ice would go down a north-south running valley, because the ice wanted to go there anyway and there was already a valley, it would just deepen out those valleys. It's very much like when you're driving in mud season, and the whole trick, of course, is you're trying to stay out of the ruts, right? But once you're in the ruts, you can't get out and you just make it worse for yourself and everybody else. Well, that's what the ice would do. Even if it didn't want to go in the valley, it just deepens it out. So this is the Valley of Vermont, north of Manchester. This is a south-facing cliff here. When the ice would stall, remember the ice is kind of like, it's flowing, it's kind of a conveyor belt, and what's it carrying? Rocks, sands, gravels, pebbles, cobbles, clay, everything. But as it gets far enough south and starts to melt out, it's just dumping this stuff. And as it dumps, it's creating these structures called moraines. And these are just small moraines. This is in Dorset, I think, or Mount Tabor, somewhere just north of Manchester, I guess. When the ice melted out, because it had contained within it rocks, sands, gravels, boulders, and it melted, it would just dump the boulder anywhere it happened to be. This is called a glacial erratic. So sometimes you'll find these huge rocks in the middle of the woods of a different bedrock than the local bedrock. They used to think it was Noah's flood before they came to understand that this was glacially put there, and only 18,000 years ago. So this is a snowbank in March or April, and you can see it's got a lot of sand and pebbles in it, and it's melting out. This is on a micro scale. And when it melts out like that, it's called glacial till. So most of our upland areas have glacial till on the bedrock, on top of the bedrock. So that's very, very common. That's why when farming around here was so difficult. And here you can see, who wants to farm this? Let's move to Ohio, right? Another thing that the glacier would do is when it ran right over bedrock, because embedded in the bottom of it were all these pebbles, rocks and such, it would create glacial striations. These are caused by the glacier moving southward. Here you can see it again. It's a little hard to see sometimes. It helps to do it in the late afternoon sun. In some places, when the glacier melted out, the till was very thin. So here you've got like 6 inches of soil, right? But go just a mile and a half away, and the till is like 10 feet deep.
Now where is this?
This is in Putney.
This is in Putney?
Yep. And you can see why they abandoned the road. I mean, it just washes out. Look at this.
In the previous slide, I think that's up near Putney Mountain.
It's up near Putney Mountain.
There's very distinct crevices and going this way. Now, is
That's-
that from the glacier itself?
Yeah, well, when you're looking on a place where people could have been traveling with vehicles, sometimes it's possible to mistake like a dragged metal, because I know exactly the spot where it is. So you want to, when you're looking for the striations, you want to go to a place where you know there couldn't have been any vehicles across it that might have possibly confused.
No, the really deeper set ones are obviously around here.
Yes, you would also need to have them going pretty much the right direction as well. So you have to sometimes, in science, you have to eliminate the alternate explanations. So you have to be able to rule out the other explanations. So you're trying to look for one where you know you couldn't have confused it with anything humans might have done, because I've run into this problem. So there it is. So sometimes the till is thin, sometimes just randomly the till can be very thick. One of the hills that gets created by glaciers are drumlins, okay? And these are egg-shaped hills. If you saw them from above, they're egg-shaped, and the longitudinal axis of the drumlin is in accordance with the flow of the ice, the direction of the flow of the ice. So you can tell which way the ice was flowing by the direction of the drumlins. Drumlins come in swarms. So this is a drumlin map of southern New Hampshire. And you can see there's tons over here, there's tons here. If you fly out of Logan Airport and you see all those islands in the harbor of Boston, those are all drumlins, okay? Because that area at the time of the ice was not below sea level. And why was it not below sea level? Because so much of the world's liquid water was caught up in these ice masses in the northern hemisphere when they were at their big size, that worldwide sea level everywhere dropped by as much as 400 feet. That's a lot, right? And so it wasn't just in the temperate zones that was happening. That was happening in the tropics too. So all kinds of places that now are underwater at that time were above sea level. And the rivers of the world had to have their river valleys make sense flowing to that lower sea level. So like there's a underwater canyon called the Hudson Canyon offshore of New York City heading off southeast that was the river valley at a time when the sea level had been lower, which was for much of the last 2.5 million years. I know in Dummerston where maybe 20 years ago they were proposing to put a landfill. The engineers drilled down, and even though today the Connecticut River's at 221 feet or something like that, they didn't hit bedrock till they got to 35 feet above sea level. So there's an underwater canyon in the valley of the Connecticut River there that's filled in now with soft sediment. So nothing is indicating it, but it's there. And this is Brattleboro, the Connecticut River here. The ice of the most recent ice advance reached its maximum 18,000 years ago. At that point, all of New England, north of Cape Cod, north of the north shore of Long Island, was under ice. New England looked like Greenland or Antarctica today. There were no plants, no people, no nothing. It was a waste, from a human standpoint, a complete icy waste, inhospitable. But beginning 18,000 years ago, it began to melt back, and as it melted back, it would create these things called pro-glacial lakes because of all that meltwater, right? And these were a common phenomenon. And so as it melted back here in Vermont and New Hampshire, the Glacial Lake Hitchcock was created. Glacial Lake Hitchcock was dammed up by a glacially created dam south of Hartford, Connecticut, and it ran ultimately all the way up to St. Johnsbury, okay? Now, if you think of today, St. Johnsbury's maybe 600 feet or so above sea level. I don't know the exact number. It's something like that. Hartford's maybe 100 feet above sea level. There's no evidence for a 600-foot high dam south of Hartford. It was just a small natural dam. How could you have a lake if the land is doing this? Well, the ice still existed to the north. It was so heavy that it depressed the Earth's crust enough to make the Connecticut River Valley be level, not sloping. And so that's how Glacial Lake Hitchcock could exist. As the ice continued to move northward, just like when somebody gets up off a couch, the lake drained, and so Glacial Lake Hitchcock came to its end. There's no evidence of a catastrophic blowout through that dam. It didn't seem to do that. There's no blown out section of river valley south of there. So it was some kind of gradual event. And here in the Brattleboro area, the lake went up the Connecticut River, but it also extended up the West River all the way to Newfane Townsend area. And here, looking at Brattleboro from Mount Wentastic in New Hampshire, everything below this level would have been underwater. So the shoreline level of Glacial Lake Hitchcock was the same as the parking area for the Brattleboro Hospital. So everything below that. So if you wanted to go shopping at Main Street or the Co-op, you forget it. You'd need scuba gear. So here, everything would have been below the level of that cupola. So this would have all required submarine travel. And over here on Wantasticate, this was the lake level. So above this would have been dry land. This is Bellows Falls. I don't know what their real estate people decided, but everywhere where they put the houses would have been underwater. So let's just hope the lake doesn't return anytime soon. So this would have all been underwater here. And here is the Cold River. This is in Bellows Falls, Fall Mountains over here, the Connecticut River's here. We're looking southeast. This is the delta of the Cold River. So this would have all been underwater here. And that area is now being mined heavily for sand and gravel. Here you can see, looking from Fall Mountain again, this is shoreline all along here. So everything else would have been looking south, would have been a long, narrow lake where you had sand deposits from these lakes. Pines often flourish. And one of the things that the glacial lake Hitchcock created, that these other glacial lakes did too, are these sequences of layers called Varves. And what they represent is the years of deposits at the bottom of the lake, where during the summertime, when the surface of the lake was liquid and you had a lot of erosion happening, you'd get a thick, lighter layer. And then in the wintertime, when the surface of the lake was frozen over, you'd get a thinner, darker layer. So each couplet of Varves represents 1 year, and you can count them like tree rings. So here you can see, looking from Fall Mountain down onto Bellows Falls today, when Glacial Lake Hitchcock finally emptied out. At first there were all these soft lake bottom sediments filling the valley, but then we know in New England every so often we get a really killer hurricane or something that in those days, with no dams to protect from flooding, would lead to huge amounts of erosion happening. And so maybe here was the original lake bottom surface, but after an Irene event, a huge, more centralized section of the valley would get eroded out, leaving behind a terrace, an abandoned terrace that had been earlier where the river valley was, but now the river valley's dropped down to here. And then in a subsequent hurricane, you'll get another huge erosion event dropping down the valley's level to another lower point, leaving behind abandoned terraces, then another one, another abandoned terrace, another abandoned terrace, until finally you hit bedrock, right? And when the river hits bedrock, yes, it's still eroding through, but it's now eroding really slowly by comparison. So what you get, though, is a stair-step pattern of terraces. You get it in Bellows Falls, you get it in Brattleboro, you get it in all the towns up and down our valley. And so one of the reasons the streets are so crazy in Brattleboro is they're trying to connect all of these terraces that go higgledy-piggledy in the ways that no human would have come up with, but it's what the Brattleboro real estate industry had to deal with. Here you can see, we've got a terrace here, and this car is trying to figure out, how do I get up to here? Because if you're from out of town, it can be hard to do. This guy's figured it out. Okay, so we've now covered 500 million years up to the present, but we're going to now have a slight preview of where we might be going in future years. I mean, nobody really knows, but let's just take a chance. What does my knee poking through these blue jeans have to do with our geological future? Well, I think you can all understand that once upon a time the denim fabric covered my knee, but that over the years it eroded away from abrasion, right? And so my knee is poking through what used to cover it, right? Well, this is a bedrock map of northern New England, including the Adirondacks. And here you could think of these pink-colored rocks as being like my blue jeans, and they used to cover the Adirondacks, okay? But what's happened is there's a hot spot underneath the Adirondacks that's pushing the Adirondacks up that's caused the overlying pink-colored sedimentary bedrock to erode away, just as my denims had eroded away. And so the Adirondacks, even though they're very old bedrock, over 1 billion years old, they are a very juvenile, very young mountain range, and they are poking right through that once upon a time covering rock, just the way my knee poked through the blue jeans. So they're still rising. The Adirondacks are rising at a rate faster than the Swiss Alps. So I don't think any of us are going to live long enough to see what happens, but it might be we have a high mountain range forming just to our northwest, made out of very ancient bedrock, but very young topography. So that takes us right up to not just 500 million years in the past, but right up to the present and a little bit of the future. And that's it. So, does anyone have any questions? Yes.
You've been to Miner's Ledge on the New Hampshire side.
Mine Ledge, you mean the white? Yes.
Yeah. From what I understand, that is a direct result of the reservoir that you just spoke about that drained down the Connecticut Valley. Because for years I was perplexed. I thought, how they didn't have the technology back then to earth out all those giant boulders, but apparently the thermofrost, when the melt broke the dam and the Connecticut River Valley was draining, created a turbo effect where those giant granite craters just came out of the side of the mountain. And that's why you look down the cliff and you see hundreds of these giant boulders.
Well, actually, yeah, it was not Glacial Lake Hitchcock draining.
It wasn't?
No, that's just frost action. Okay, rocks have cracks, right?
Yeah.
Okay, water loves to go into cracks, yes? And what happens to water when it freezes? It expands, yes. And so if you have, especially a southwest facing face like that, gets a lot of sunlight, and some kind of rocks shatter more easily than others, you just get it shattering from ice expansion, frost action. And so mountain ranges, you'll see these big shattered rocks. If you go to the base of Cannon Mountain, where they love to climb up the cliffs, you just see this enormous amount of shattered rock, or there's a lot in the Adirondacks. White Mountains have a ton. So that's what you're seeing there. Yep.
It contradicts what a geologist had said in...
That's too high in elevation to be Glacial Lake Hitchcock. We're talking about Mine Ledge with the white bedrock, yes? Yes, it's too high in elevation.
All right, well, thank you.
Yep. Other questions? Yeah.
And sometimes walking around in the woods, you see these fairly small lumps. And are those drumlins that you were describing, or sometimes you think it's where they were digging, quarrying something, and they...
Oh, you're talking about pillow and cradle. And what happened? It's not geology. It's meteorology, basically. We get hurricanes around here, or big storms, okay? And if you have big trees that have big root balls, you'll see them. Sometimes they go over, and the roots are sticking up like this. Well, eventually everything deteriorates, and so that leaves a lump of soil there. Meanwhile, there's a cavity right next to it. Okay, so that's pillow and cradle. So it's not caused by geology. It's caused by windstorms. Yes, and sometimes you'll see a whole place that's like that, and it must have been a really bad storm that did that. So, whoops. I'm just going to put this. Thank you. Any other questions? Yes.
We live in West Guilford, and there's a stream that divides our property from our neighbors. We have a ridge on our side, and they have a ridge on their side. Their plant life on their side is all, it's that dirty brown marble, and it's maidenhair fern.
Oh, yes.
All those things that say, ooh, nice limey soil. Our side, we're talking hemlocks and oaks.
Yeah.
It's like there's this dividing line right down our little stream bed.
Are you near the eastern part of the town?
West.
Okay. Well, it could be there's different formations, and so yeah, very possibly, very likely, that is a geologically created difference. Although, even on the richest bedrock with the richest soil, if hemlocks and other conifers are there long enough, and they can grow in those conditions, their acid needles will change the soil to such an acid condition that even though the underlying bedrock's excellent, those last bit of topsoil is so acid that things like maidenhair fern couldn't get going. I've seen that in northern Vermont, where it was like a stream that was incised 5 feet down to bedrock, and right along the bedrock the pH was 7. It was a really rich soil, but as you went up, because of the forest history, it got more and more and more acidic from that forest history. And so so it can happen that you have really great bedrock, but the soil right there.
Yeah, but further up the ridge line, the hemlocks peter out. Well, we still don't have maidenhair fern.
No, maidenhair fern really indicates you have excellent soil. So, right, you can't miss. Yes.
That it could be such a, right there.
Yes. Yes, and around here, even though the geologists have put everything into these different formations, even within a single formation, the different layers can be very different, one from another, for another, for another. Yep.
I was wondering about this level ground. Is level ground the optimum if there were forces, geological forces? What actually makes level ground as opposed to?
Well, gravity, I mean, everything wants to get absolutely planar, and but, you know, the rocks in some places are really hard, or you don't get much rainfall. I mean, the Canadian Shield to the north, say north of Lake Superior up there, the rocks are really old, billions of years old. They've had billions of years of erosion. Are they down to absolutely flat? No, they are not. They're really hard rock. They may not be all that high, but there's you know, really hard rock, even with billions of years of erosion, hasn't eroded to absolute flatness. But the softer rocks are rocks that are getting deposited, like on the coastal plain of the South Atlantic. There, the rocks were laid down very flat, and then sea has come on top of them and deposited things. It's almost flat. So sometimes you will get almost flat, but if the rocks are hard enough, they might not get there. I think Greenland has the oldest rock of all. It's 3.8 billion years. It's still hilly. Okay. Yeah. Oh, yes.
So Roger, that was a great talk, really brilliant. I think you brought things down to a level that we can all understand. And I now know why they refer to you as a rock star. And I would say this was a gem of a talk. But my question is a little bit around the edges. You talked about not just changes in geology, but changes in climate that we're having.
Oh, yes.
And so I just wondered if you could put in context what people are saying today about climate change.
Sure.
Some of our leaders say that climate change doesn't exist, and I just wondered if you could help us think about this a little bit in terms of your presentation today and how we might think about that.
Okay, well, the climate is changing right now, warming at a rate right now the climate is about where it was 6,000 years ago. In other words, 6,000 years ago the climate warmed up from the Ice Age, and then it started to cool again, and then recently we've warmed it up again to about where it was 6,000 years ago, but we're going to keep shooting upwards. If you go back through the history of the Earth, over most of the last 500 million years, believe it or not, the worldwide climate has been warmer than it is right now. So by a standard of the last 500 million years, we're still in a cool period because we have big ice caps on Antarctica, big ice cap on Greenland. That's fairly unusual for the last 500 million years. But if we look at the last 2.5 million years, when there have been ice advances and retreats, today's climate is unusually warm. So depending on which standard you want to use, we're either unusually warm or unusually cool. But what's really different here is the rate of change of the climate is so fast that it's going to have devastating effects on the ecosystems, because the plants and animals and all of that, their complex webs, are not going to have too much time to do much adaptation. We are very probably engaged in an extinction event now caused by us that will rival the extinction of the dinosaurs in terms of what the effects will be. And that was a devastating change that came literally out of the blue. It came out of the sky, right? It was a meteor that hit the Earth where they found the crater in the Yucatan Peninsula down in Mexico. How did they find it? All right, I'm going to back up. I worked for many years on the NOVA Science program, and in 1980 I worked on a film about the extinction of the dinosaurs. And who was the scientist who, together with others, came up with that theory? It was a man named Luis Alvarez. Luis Alvarez was one of the 4 people who armed the actual atom bomb, right? He was a physicist, one of those physicists from the 30s and 40s, and he won the Nobel Prize in Physics in 1968. he was at Berkeley, a professor. After he retired, they gave him an office because he'd won the Nobel Prize. Okay, you get an office even if you're retired. And he was doing his little retirement projects. He had a thing about gamma rays. But he had a son named Walter who was a geology professor also at Berkeley. And Walter, the son, the geologist, came to his father and said, "Dad, everywhere we look in the world, where the dinosaur rocks come to an end, because they're older, they're below, and the mammal age rocks begin, they're the younger ones, we find this dark layer, this black layer. We find it in New Zealand, Italy, Texas. What is it?" So they start looking. They realize it's got a lot of this element called iridium. And iridium comes either from meteors or it comes from volcanic eruptions. So they start coming up with hypotheses, and the one that seems to fit is a meteor hit the Earth 65 million years ago, 66 million years ago. And lo and behold, that theory has held up. It may have incidentally also caused huge volcanic eruptions at the same time from the force on this side of the planet in India, the Deccan eruption. So between them, they so altered the atmosphere, altered the oceans, altered everything. They wiped out every land animal of any size at all, including all the dinosaurs except the birds, who are today's dinosaurs, okay? They continued on. Turtles and alligators made it because they were underwater for a little bit. But basically, our little rodent-sized ancestors, the mammals, came into being because of that. And so Luis Alvarez came up with a retirement project that I think you could say had more consequence in science in a field that wasn't his own field at all when he was over 65 than what he'd done to get the Nobel Prize for. So sometimes even an old person, yes, can do amazing things. And the only other example I know of somebody who did something quite that unexpected at age 65 and over is Colonel Sanders of Kentucky Fried Chicken. He started Kentucky Fried Chicken with his very first Social Security retirement check. So, yes, it's very encouraging. So, anyway, yes?
What stopped the volcanic pushes? I mean, why didn't they continue to push all, why are there more today?
Well, there are some today that are happening, but it's all very slow motion, okay? So a volcanic island chain would be the Japanese islands, okay? Basically, when Pangaea, which was the supercontinent, where at one point 200 million years ago, 225 million years ago, all the world's continents were one continent, and all the world's ocean were one ocean called Panthalassa. And what's happened is, beginning 200 million years ago, Pangaea began to split apart, and basically the Americas started heading westward, Europe and Asia were starting to head eastward, and they're both converging on the Pacific Ocean, okay? So they're moving towards each other, but they got a long ways to go before they're going to hit. And so as Asia is moving eastward, or it is basically colliding with some of those offshore island chains that are there. So there's a process that's kind of got some similarity to what we were going through back, 460 million years ago. If you look at a bedrock map of like the western United States, so many things have or western Canada, so many things have jammed into it. It really, if you think of on a pond or something where you have a whole bunch of branches and leaves and stuff, and the wind blows them all up against the shore, that's kind of like what the bedrock map of British Columbia and the Yukon looks like. It just looks like everything got jammed up. And some of the things are jamming sideways. So that's what's happening here. Go back far enough. So you're seeing it, those things are active there. One of the things that was happening here at the time when volcanoes like Black Mountain were happening here is there was a whole line of them running up the state. Black Mountain may never have made it to a volcano. It might not have made it to the surface. Further north, you have the Northeast Kingdom. You have the same granites there that you have in Black Mountain here. And so if you look at them, they kind of make a nice line north-south. If you look today at the Pacific Northwest and look at where the volcanoes are there, you've got Mount St. Helens, Mount Rainier, Mount Hood, Shasta Mountain, Lassen Mountain. Look at them on a map. They're almost in a perfect straight line. And what's happening is that subduction is coming in from the west, from the Pacific Ocean. When things get down 50 or 100 miles down, blobs of hot magma come up, and because they reach that certain depth coming from the west, at the same distance interior from the shoreline, all these volcanoes are rising up. Something like that was happening here 400 million years ago or so, 380 million years ago.
I think we're going to end it there.
Okay.
Roger, this was, as I said before, stupendous, terrific, and I hope that everyone enjoyed this really as much as I have.